Hello, welcome to my channel Pradeep Sir Online Classes. Today's class is based on the numerical analysis. So in 12th standard there are 15 chapters. I decided to take a particular books that's available on the market. Different books are available, so you can choose any one of them. And let's start with a particular series named the Numerical King. The Numerical King first day, and this one I taken for this session. I taken a particular book that is H.C. Verma Physics. So how to solve H.C. Verma volume 2. Parallelly I continued volume 1 also. So the first chapter is electrostatics, and mainly for today's students, mainly the problem is on numericals, and I think which book I choose. So I suggest you that any one of the books, that it may be Resnick's Holidays or the electro concepts of physics, S.L. Arora comprehensive physics, Irodov or concise physics, or McGrew-Hill, Sengage, it may be Sengage, the most conceptual physics books. So I taken the most renowned and the famous physicist, that is H.C. Verma, H.C. Verma, the HOD of Kanpur IIT, and he is most humble ones. And so this episode continued for a particular days, and I chosen that per day we take 15 or 30 numericals basically, and clear all the concepts given at a particular think that a particular author are always completed all the concepts in a particular syllabus. So you can choose any one of the books, and most probably nowadays in conceptual physics, concepts of physics by H.C. Verma, it will be better. So let's start with electrostatics, and the first numerical of the electrostatics is find the dimensional formula of epsilon. So what is dimension? You have clear it, that what is the dimension? Dimension actually the exponent of the fundamental physical quantity within a particular derived works. So here the derived quantity is epsilon naught, and the dimension is m to the power minus 1, l to the power minus 3, t4 and a2. That is, here the dimension, the fundamental quantities are here the fundamental quantities are m, and then the length and time and ampere. So there are 7 fundamental quantities as well as 2 supplementary quantities, that is length, mass, time, temperature, current, candela, luminous flux, that is, and the amount of substance. So here there are 4 fundamental quantities whose exponents are the minus 1, minus 3, 4 and 2. So the dimensional formula is this one, and the dimension is minus 1, minus 3, 4 and 2. And so the first you have to define or clear the concepts of dimension. So dimension are the exponents only, and all the numericals given here from 1 to 15, the concepts are taken from only Coulomb's law. So basically in first questions, I repeat again, this is only the concepts of Coulomb's law, and the Coulomb's law states that this force is proportional to the product of the charges and square of the distance, that is inversely proportional here. So the equations is F equal to 1 by 4 pi epsilon naught So the equation is F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. And this is the proportionality constant. So here epsilon naught 1 by epsilon naught is taken, that is F R square by Q1 Q2. So the dimension 1 by epsilon naught, the dimension of epsilon naught equal to dimension of F R square by dimension of Q1 Q2. So dimension of epsilon naught equal to, you have to change the numerator and denominator portion, that is dimension of Q1 Q2 by the dimension of F R square. So dimension of Q equal to A into T, and again Q2, Q1 Q2 all the charges, so AT into AT by force, dimension of force is MLT minus 2, and this total conceptual the concepts about the dimensions is taken from the base level, that is the 11 or MLT minus 2 L square. So here M to the power minus 1, that is M is in denominator portion, so when it goes in the numerator portion it is minus 1, and here L and L square, that is L cube, and it when it goes to the numerator portion it will be minus 3, and T or T minus 2 when goes in the upper case, then it is T square. So T and T square, this T to the power 4 and A to the power 2. So minus 1, minus 3, 4 and 2 are the exponents of this physical quantity epsilon naught, and the dimension of epsilon naught is m to the power of this. This is the dimensional formula, and always the dimensional formula taken within the third bracket, and the dimensions are the exponents, that is minus 1, minus 3, 4 and 2. So the first questions mainly depends mainly if you have the clearance of these dimensional concepts, that you can do this. So the second one, second numericals. Second numericals is basically about the main concept of about the ideas or concepts of the electrostatic force. So you know that most of the students are clear about the concepts of weight, by about the feelings of weight. Suppose if a student is 80 kg, then its weight is 80 into 9.8. It is the average value of acceleration due to gravity. So here the problem is a charge of 1.0 coulomb, and this is the significant ones. So 1 is the certain digit and 0 is the uncertain limit, so you must take 1 coulomb. So a charge of 1.0 coulomb is placed at the top of your college building. So 1 coulomb charge is placed at the top. Here this is the college building. And it is in the on the top of the college building. 1.0 coulomb charge is kept, and this is the another building, that is your building, and it is 1.0 coulomb, and the distance between the two buildings is 2.0 kilometer. Here all the figures respected AC Verma taken as 2.0, that is the significant figure is 2, that is 0 is the uncertain limit, that it may be 2 point something, but you have to take 2 kilometer almost. So 1.0 coulomb and 1.0 coulomb, and the distance is 2 kilometer, that is 2000 meter. You have to change a particular SI unit system. You can't replace, can't place it with a particular multiples or sub-multiples, so you have to change a particular SI unit. So 1 coulomb, 2 charges are kept at a separation of 2 kilometer. Here the questions, and this is placed at your top your college building, and another equal charge is top your house, and take the separation between the two charges to be 2.0 kilometer. Find the force exerted by the charges on each other, and that's right, find the force exerted by the but the next line is how many times of your weight is this force. So how many times of your weight is this force? This implies that the Coulombian force, you have to compare, but you compare the Coulombian force as well as with your own weight. So about the Colombian force, you can clear your concepts in the view of your weight. So first of all, applying Coulomb's law, here the formula is given. Applying Coulomb's law, F equal to kappa. Kappa is the Greek alphabet, and most of the books use K, and the K, another K, that is the dimensional, the dielectric constant. So here kappa you can take as Greek alphabets, the proportionality constant. So F equal to the sine kappa Q1 Q2 by R square. So this proportionality constant gives a value 9 into 10 to the power 9 you have taken always, and Q1 Q2 is 1 into 1, that is 1 coulomb divided by R, the distance between the two charged particles, that is 2000 meter. So 9 by 4, and always remember when you calculate a particular figure, that is 10 to the power 9 divided by 4 into 10 to the power 6, that is 9 minus 6, that is 3. You apart all the numeric value in a particular positions, and the zeros, that is the limits or the magnitude of the powers, and is apart, that is 9 by 4 into 10 to the power 3, that is 9 by 4 means 2.25 into 10 to the power 3. So here the Coulombian attractional force or repulsional force it may be, when 1 coulomb positive and negative charges, the fundamental law of electrostatics tells about the nature of the forces, here positive and negative charge, and here two equal positive, so the repulsion force of these two charges you have to take. The next one, so the repulsion force between these forces is 2.25 into 10 to the power 3 Newton, and suppose your weight is 80 kg. If your weight is 50 or 60 kg, then in place of 80 kg you put 60 or 50 kg. So F suffix E, that is it represents the electrostatic force and divided by your own weight. So in place of electrostatic force you have to substitute 2.25 into 10 to the power 3 divided by, is it not clear? Okay. Okay, so Fe equals to 2.25 into 10 to the power 3 divided by your own weight, and you have to substitute here as the value of G, that is 9.8. You taken the average value of this, or you have to take 10 kilometers, that is 80 into 10. So Fe equals to 2.25 into 10 to the 3 divided by your own weight. So this gives a result 0.028 into 10 to the 3. That is, you have to take 2.8, that is the numeric value, and here is so 10, as this point goes 2 units from the right side. So 280 approx. So 280 tells us and remind that particular points, and how many times of your weight is this force. So how many times of your this weight is with your own weight. So 280 approx, that means that the electrostatic force for that particular repulsion force 1 coulomb and 1 coulomb from the college building and your building is 280 times of your own weight. So how much force 1 coulomb exact actually we clear from these concepts. So the next questions. So from two questions, 1 and 2, first of all, question number 1 that gives us the knowledge but clear the concepts of dimensional analysis, and the second one is the concepts of Coulombian repulsion force, as well as it compared with your own weight, that you have to realize how much this force attract. So the next question is, at what separation should two equal charges 1.0 coulomb each, at what separation should two equal charges be placed so that the force between them is equal to the weight of a 50 kg person? So questions is same, but the difference is from 2 to 3 is the separation between the here it is calculate the separation, and the for the question number 2 it is force. So at what separation should two equal charges 1.0 coulomb each be placed so that the force between them equal to the weight of a 50 kg person. So this force here, force is given, and the force is 50 into 9.8. First of all, G is the main problem. G, one of the students takes G as 9.8 and the another student take 10. So 2 is right, because G, the value of G is varies at place to place. So you have to take the average value, or for easiest calculation you can take 10. So F equal to 50 into 9.8 Newton, and F equals to 1 by 4 pi epsilon naught, as it is from the Coulomb's law. F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. So F equal to 50 into 9.8 and 1 by 4 pi epsilon naught. In place of 1 by 4 pi epsilon naught, you have to put 9 into 10 to the power 9 into Q1 Q2, 1.0 into 1.0 by R square. So here you have to calculate the separation between the two charges. So R square equal to this one, and you can calculate this multiplied by 9 into 1 divided by 5 into 9.8 into power 10 to the power 9 by this, and this gives the result 4.3 into 10 to the power 3 meter. So 2 and 3 questions, number 2 and 3 are similar in the concepts, but one question is to calculate the force and the another is the distance. So question number 4. Two equal charges are placed at a separation of 1.0 meter. Two equal charges. So you have taken as Q and Q. So Q square. Two equal charges are placed. Always F is directly proportional to the product of the charges. So Q into Q square, that is F is directly proportional to Q square here. So two equal charges are placed at a separation of 1.0 meter. That is again the significant digit is 1.0. So 0 is the uncertain digit and 1 is the certain digit. What should be the magnitude of the charges, so that the force between them equal to the weight of 50 kg person. So my God, 50 kg, 50 kg, 50 kg, and so F equal to 50 into 9.8 and F equals to 9 into 10 to the power 9 into Q square. It is not 9, as it is, this is the difference between 9 and Q square. So 9 into 10 to the power 9 into Q square divided by 1. Here it is given 1 meter is the distance of separation. So Q square equal to F means 50 into 9.8 divided by 9 into 10 to the minus. So this gives the result 2.3 into 10 to the minus 4 coulomb, or you can write 0.023 2.30 into 10 to the minus 6 or microcoulomb units. You can convert it. So this is enough, 2.3 into 10 to the minus 4 coulomb. And the question number 5, find the electric force between two protons separated by a distance of 1 Fermi, and the protons in a nucleus remain at a separation of this order. So nucleus, so nucleic separation is 10 to the power minus 15 meter or 1 Fermi, but the nucleus, but the size of the atoms is at the order of 10 to the power minus 10 centimeter here. So within the nucleus there is a lumps of protons. So if we take it is not the separation of the proton and the electrons are given within the nucleus. So you have to confine within the particular nucleus, and the largest separations mean its diameter, and diameter is the largest separation. So find the electric force between two protons separated by distance of 1 Fermi. The distance is given. So in a nucleus remain at a separation of this one. So if the equation says this is the charge proton and proton. Proton means the charge of the proton is 1.6 into 10 to the power minus 19, and it is, all of you know. So 9 into 10 to the power 9, this is the value of kappa, the proportionality constant, into Q means Q square divided by the separation of the nucleus is 10 to the power minus 15 meter. So this is F equal to 230 Newton. 230 Newton is the separation, is the repulsion force between two protons within a particular nucleus. So the next question, two charges, these Coulomb are separated at a separation of 10 centimeter. Where should a third charge be placed such that it experiences no net force due to these charges? This is the different cases arises such problem. So when we solve this type of problem, we have to think the charges is the charges is the positive ones, and this one is also positive. And if this charge is positive and this is negative, then the equilibrium position is changed. So what is equilibrium? What are the different cases? At first we observe that type of numerical problem and how these are related with a particular situations. So 2 into 10 to the power minus 6, and here it is also, this is the order means 10 to the 6 means microcoulombs. So if we take micro as q, then 2q, and this is q. So 2 into 10 to the power minus 6, and here 1 into 10 to the minus 6, two charges are given and the separation is 10 centimeters. So 2q, if you have to take into consideration the knowledge of charge, that is point charge, as well as the test charge. So where should a charge, here it is given a charge, not test charge. So suppose I put a charge of amount capital Q units here. Here is the position. This is the position. Case number 1, if the two charges are given 2Q and Q, and if we placed a charge, another charge capital Q here, then these charge repel these charge in a particular direction that is given here, and these charge also repel these charge to that particular positions. So it may be total system is in equilibrium if these two forces are equal. But for the second one, if we notice that here, if we place the charges, particular charges in a particular these positions, then these charge apart repels along this direction, and these charge also repel along this particular direction. So these charge move in this particular directions. So this is not the exact positions, and if we place here also for the case number 3, that is also same with the case number 1. So case 1 is the exact position, means if this charge repel this for along this direction, and this charge also repel that particular charge in that direction, and if the two forces are equal, then this charge and this one and this one are equal. So first of all, for this equilibrium condition and this type of problems, you have to take into consideration that particular trial and error method. That is case number, what are the different cases arises, and if it may be this is the charge, the nature of the charge, it may be negative. So here you have to check it. So the problem is there are two charges, and where the third charge is placed so that the total system is in equilibrium. So here is the position, and the repulsion force between the two charges is kappa q1. This is the value, and q2 by x square, and for this pair this is equal to capital Q small q by 10 minus x whole square. So kappa and kappa cancel each other, and here small q and capital Q, here also small and capital Q. So this also cancel each other, that is here 2 remain, and 2 divided by x square equal to 1 by 10 minus x square. So if we take this square root, so root 2 divided by x equal to 1 by 10 minus x, and this is the easiest process. If you square 10 minus x whole square, then it is too much critical. So root 2 divided by x equal to 1 by 10 minus x. or you can cross multiply this one. So 10 root 2 minus of 2 root 2 into x, this is equal to x, or x equal to 10 root 2, and root 2x when goes in this side, particular this side, you can common it, that is root 2 plus 1, so root 2 plus 1, and the root 2 value of root 2 is 1.414, so 10 root 2 divided by 1.414 plus 1 and gives result 5.86 centimeter. So 5.86 centimeter is the distance, and this is from the large one, large charges, that is 2q, not q. And if the answer is given from the smaller ones, then you have to minus it from 10 minus this one. 10 minus 5.86. So you have to write here that from larger one. So it is this like problem are always remains in a particular exam. So it is the different another numericals here. We change the particular charges with the nature of negative. Suppose the second charge in the previous problem is minus 1.0 into 10 minus 6 centimeter. Sorry, Coulomb. So suppose the second charge in the previous problem is minus 1.0 into 10 minus 6 Coulomb, and locate the position where a third charge will not experience any effect. So then 2q charge here, and here is minus q, and if we place again in that particular position, that is in the previous one, so these charge attract this positive charge, and this repel, and the charges goes along this direction. If here it is position, then these charge attract this one, and these charge repel this one, because positive and positive repel each other, and negative positive attract. So this particular position, the charge goes from this direction. But if we take the charge is here, then these minus charge attract in that particular direction, and these charge repel these charges in a particular direction. So it is the situations of equilibrium position. It may be. So the repulsion force, the repulsion between these and these one is kappa q1 q2 by r square. This is the distance of 10 centimeter, and this, and here you can't change that particular units, because this unit and this unit cancel each other. So kappa qq, this and this kappa q2 by x square. So here q and q cancels q and q, and kappa cancels kappa. So root 2 divided by 10 plus x equal to this one, or when I then cross multiply this and this one, and root 2 plus 1, root 2 minus 1, x equals to 10, or x equal to 10 by 0.414, that is 24.1, and you have to specify that particular direction, that is from smaller one. So if the answer is given that it is from minus 1, okay. Next, question number 8. Two charged particles are placed at a distance of 1.0 centimeter apart. What is the minimum possible magnitude of the electric force acting on each other? Two charged particles are placed at a distance of 1.0 centimeter apart. Two charged particles are placed at a distance. What is the minimum possible magnitude? And this is the main vital point. What is the minimum possible magnitude? So when the force is minimum, this is the questions. When the force is minimum, when the charged particles, when the magnitude of charged particles is also minimum, that is the least value of, from the quantization of charge, we know that q equal to any, that is q equal to any means always the charge are in a integral multiple with a particular least value of electronic charge, that is 1.6 into 10 to the power minus 19 Coulomb. So quantization of charge tells about the nature that if I give you a 100 rupee note, then it consists of 100 into 1 rupee, that is 100, or 100 is the numeric value and 1 rupee is the quantum. So 100 is the q and 100 is the integral value, that is n, and E is the charge that is here compared with that particular value 1. So quantum means charge gathered in a particular, when we rubbed with a particular substance, the large number of electrons is transferred from one body to another. So quantization of charge tells us the least nature of charge is 1.6 into 10 to the power minus 19. So what is the minimum possible magnitude of the electric force? That is here, this is the funda of this problem. You have to take the value is E. E means 1.6 into 10 to the power minus 19. So when E are separation 1.0 centimeter apart, then the force is kappa Q1 Q2 by R square, and here kappa is 9 into 10 to the power 9 into E by R. R is 1 centimeter, that is 1 by 100 meter square, and the calculation is too much simpler, that is 2.3 into 10 to the power minus 24. And here the order, as I say, from the first one, if the order, that is the order of magnitude is given, that is the power of 10, then you separate this value and all the numeric value, that is 9, 1.6, 1.6 are taken and multiplied with each other. So 2.3 into 10 to the minus 24 Newton. Next one is estimate the number of electrons in 100 gram of water. 100 gram of water. Suppose you wakes up in the morning and your mom gives you a glass of water, that is 100 gram, it may be 250 gram as it is. And so 100 gram water, it consists of H2O molecules that contains H2O molecules, so that contains 2 H and 1 oxygen atoms. So the number of electron is for hydrogen it is 2 and for oxygen it is 8. So 10 electrons are there within a particular molecule. So hydrogen H2O, so the molecular weight, what is the molecular weight of, as you know from the chemistry concepts, the molecular weight of H2O, that is 2 plus 16, that is 18 gram. So 18 gram H2O contains 6.023 into 10 to the power 23 number of moles, the molecules. From the mole concept, we know that the molecular weight contains this number of Avogadro number of molecules. 18 gram H2O contains 6.0, that is the Avogadro number of these molecules. If you take that the atomic number, then this contains this number of atoms, and this volume is 22.4 liter. So 18 gram H2O contains 6 point, this is the water, and the 2 electron for hydrogen and oxygen for 8 electrons. So there are total number of electrons is 10. So 18 gram H2O contains this number of molecules, 1 gram or 100 gram, unitary method. So 6.023 10 to the 23 divided by 18 into 100. So this is the value, and the number of electrons is each molecules contain 10 electrons. So the number of electrons is 10 into the answer here. The answer is given and this put substitute in this place. So 10 into this one or this into answer again, because the charge for electron is 1.6 into 10 to 19. So this is 5.35 into 10 to 6 coulomb. So little about concepts are clear. For the question number 9 is about mole concepts. You have to clear the concept, that is molecular weight of every substance contains this number 6.03 Avogadro number of molecules. So hydrogen, for hydrogen the molecular weight, that is the mass number of hydrogen is 2 and the 16. So 2 plus 16, that is 18 gram, or 18 gram H2O contains this one. This is the unitary method, so clear. So next, suppose all the electrons of 100 gram water. So from this question 10 tells about, and this is the combinations of question 9 and 10. So suppose all the electrons of 100 gram water are lumped together to form a negatively charged particle, and all the nuclei lump together to form a positively charged one. So this is the concepts of conservation of charge. When we rub two substance, then when we rub with particular two substance, then the work function, then the substance possesses lower work function. So in this concept, we cleared the what is work function. What is work function? So work function are the least or amount of energy, the minimum amount of energy that can given a particular substance to emit the outermost electron from here. So work function, for least work function always possesses positively charged, and the work function is greater about the compared with respect to that particular two substance possesses negatively charged. So electron, when electron transfer from one body to another, then the deficit of electrons of the body get positively charged and the another was negatively charged. But the number of electrons, always the charge remains, for an isolated system we can say that the charge remains constant, and the transfer of electron, that is when a body is this unit of positively charged, same amount of negatively charged occurs on the opposite pole. So this is the conservation of charge. Isolated, for isolated system, charge is conserved, it cannot be created nor be destroyed. So suppose all the electrons of 100 gram of water. So 100 gram of water contains all the electrons, that is charge value of 5.35 into 10 to the power 6 coulomb charge. So this value is this amount 5.35 into 10 to the 6. So these and this amount charge are lumped together because every molecules are electrically neutral. So these and this attractional force, so this is the plus and this is the minus charge. So if equal to kappa q square by 10 by 100, this is 10 centimeters, so 10 by 100 square, or 9 into 10 to the 9 into 5.35 into 10 to the 6 square and into 100, so 2.56 into 10 to the 25. So again compare it with your weight, because you have to know that this Coulombian force is much greater of 1. So for the next questions, consider a gold nucleus. So you have to consider a gold nucleus. This is the nucleus, not this is the nucleus. This is the nucleus and this is the outermost cell. And here all the protons are uniformly distributed. So these at the maximum distance you have to take, that is here given, and this is the 6.9 Fermi is the distance, it is the radius, sphere of radius. So consider a gold nucleus to be a sphere of radius is 6.9 Fermi, in which protons and neutrons are distributed. Within the nucleus we know that the three fundamental particles, electron, proton and neutron, and the proton and neutrons are distributed uniformly within the nucleus. So 6.9 Fermi in which protons and neutrons are distributed. Find the force of repulsion between two protons situated at largest separation. So largest separation means you have to take the diameter is the largest separation, and diameter of the largest separation. So this is and two protons means 1.6 into 10 to minus 19. So R equal to 6.9 Fermi. Fermi means 10 to minus 15 meter, and the diameter is the 2 times of radius. So this is the separation distance, maximum separation distance. So F equal to 1 by 4 pi epsilon naught, 9 into 10 to the 9 E into E means 1.6 into 10 to the minus 19 into this one divided by D square. So 1.2 Newton. But the question is that why this too much repulsion force can't apart this particular two protons? Why? Because all the protons always converted into neutrons and all the neutrons are converted into protons. And this is called and these conversions gives rise to a deficit of mass. This is called mass defect, and it is the topic of another chapter, quantum physics. So I will discuss later. So here the distance between the two proton is 6.9 Fermi into 2 and 1.9 Newton. And the next question, why do these protons not fly apart under this repulsion? Because this repulsion, actually all the protons are converted into neutrons, and the mass defect it arises, and this mass defect is transferred into binding force. So these force are converted into the binding energy of the protons and neutrons. So the next question is, two insulating small sphere are rubbed against each other. Oh yes, I also thank to cam scanner, because it's helped me to scan these question portions from this, and then I solve this one in my copy, and then total within the I install this one or within my digital system. So the problem is, two insulating small sphere are rubbed against each other and placed 1 centimeter apart. Two insulating small sphere. Why insulating? Because if we consider a conductor, then charge goes through it. So insulating conductor is for static purposes. So two insulating small sphere are rubbed against each other and placed 1 centimeter apart, 1 centimeter. So when two insulating spheres are rubbed together, then same amount of charges are transferred from one body to another. So here also the conservation of charges. Here also the conservation of charges, and two insulating spheres 1 centimeter apart, if they attract each other with a force of 0.1 Newton, how many electrons were transferred from one sphere to the other during rubbing? So this is called frictional electricity. Electrostatic. Electro means charge and static means rest. When the charge particle are rest, this is the branch of physics that deals with the static charge. So obviously there all the problems are based on the concepts of the Coulombian attractional force, as well as the conservation of charges, and the mole concept, and the binding energy, nuclear binding energy. Basically always compare with the three types of forces, that is strong nuclear forces, electrostatic forces, and your weight, and these comparisons much greater and builds your concepts clearly. So this session this session help you very much, I think. And if this thing, then always I say that please subscribe this channel, and you will get all the solved numericals with the different books. That is, it may be A.C. Verma, it may be Resnick Halliday, it may be concise physics, it may be Sengage physics, it may be D.C. Pandey, and many more. There's McGill Hill and Dinesh or Pradeep Science. All the different books are available on the market here. MTGs also. So you can choose any one of the book, and the question number is 12. F equal to 9 into 10 to the power 9 and q square. Here q square means two charges are similar, but the nature of the charges is different. So q square equal to 0.1 into 10 to the power minus 4 by 9 into this one. Q square equal to this into this multiplied. Here force is given, and this is 10 to the power minus 2 whole square minus 10 to the power minus 4, and the force is 0.1, so multiplied and then divided by this one gives this result. and this is the calculative process you can follow. Always you remind that all the numericals are from the basic formulas, some formulas like Coulomb's law, or it may be from the quantization of charges, but the problem is that the calculation is the main problem. So CBSE board as well as any other board is, because calculator is not allowed, so you have to always remember that if we take this type of calculations, that is 10 to the power minus 14, then you easily take 10 to the minus 7, and from 9 it is from 3, so square is out of this here. So 10 to the minus 7 divided by 3, that is this coulomb. So Q equal to 10 to the minus 7 by 3 coulomb, or Q equal to any. This is the quantization process, that always this is the integral multiple of least value of electronic charges, Q equals to. So when we rub one substance with another, then a large lump sum of electrons are transferred from one body to another. So Q equal to any, or n equal to 10 to the minus 7 by this one, and 0.21 into 10 to the power 12. That is 2.1 into 10 to the power 11 number of electrons are transferred from one body to another. So this is then next numericals 13. Numericals 13 is sodium chloride molecules is bound due to the electrostatic force. So this is electronic bond. We know that the sodium and chloride ions are attract each other with the electrostatic force and form NaCl molecules. So NaCl molecules bound due to the electric forces between the sodium and chloride ions when one electrons of sodium is transferred to chlorine, and taking the separation between the ions to be 2 point this separation, and find the separation is at the order of angstrom level. So find the force of attraction between them. Force of attraction between them. So distance is given, and the charge sodium is Na plus. That means one electron is transferred to the chlorine, and sodium contains 11 number of electrons. When it transfer one electron from from the outermost shell of sodium to the chlorine, then it positively charged, and one electrons gain chlorine atoms, and this is chlorine means 17, that is it is similar to argon molecules, and this is neon. So Na plus and Cl minus combined NaCl. So force equal to 1 by 4 pi epsilon naught, and 1 electrons in 1.6 10 to minus 19, this one divided by the distance square. So this is centimeter divided by 100 square, and this gives result this value, and by calculation process this is 3.05 into 10 to minus 9 Newton. So this is only the concepts of electronic bond, and the next one is the 14, numericals 14. So find the ratio of electric and gravitational forces between two protons. Find the ratio. Here you have to calculate the ratio of electric and the gravitational forces between two protons. So electrostatic we know from the 11th level. The gravitational, yes, in class 10th it may be it have gravitation, one chapter. So if E electrostatic equal to 9 into 10 to the power 9 into 1.6 10 to the power 19 into this by r square, and the gravitational force is, and this is the value, and this is the value. So if we compare that electrostatic force, the proportionality constant is 9 into 10 to the power 9, and for this is for the gravitational force is 6.67 into 10 to the minus 11. So this is the order is 10 to the minus 10. This is weak force, and this is strong force. So this and this one comprises to give you particular knowledge. So this into 1.67 into 10 to the minus 27 and 1.67. This is the mass of the protons, two protons given here. 6. So this gives a result of this one, or you can divide it with electron and the gravitational one. So 1.23 this is, that is much greater than gravitational force. So here after comparing these electrostatic and gravitational forces, you know that this force, electrostatic force, is much greater than the gravitational force. So today's last questions. Today's last questions is 15 questions, and I say that in every day I completed 15 questions or many more questions and solve all the numericals given in a particular book. So I solved all the numericals from the electrostatics to the semiconductor physics, from the AC Verma syllabus, and so the 15 number questions, 15 question 15 is, suppose an attractive nuclear force acts between two protons. Suppose nuclear force between two protons, attractive nuclear force between, not repulsive. Two protons, we know that always two protons repel each other, but here the attractive nuclear force between two protons when they are close compared to the 15 meter, that is in Fermi level, they attract each other. This is the concepts of quantum physics, so which may be written as F equal to C e to the power of minus kappa r whole divided by r square. So this is the knot, this is similar to that one, that is Coulomb's law, but this square law is similar to that particular laws. So square law, two of them are square law. Write down the dimensional formulae and appropriate unit. And from dimensional analysis of C and K, so see here exponential function, the exponent, this is the exponential function, so exponent always possesses unitless physical quantity. So you have take that Kr, or you may think that kappa equal to 1. So kappa r equal to 1 or kappa equal to 1 by r. R means Fermi here. So Fermi inverse or meter inverse is the unit of K. So the exponential part, always exponential part is taken as unitless quantity. So here kappa, the unit is this one, and e to the power of this is taken as 1. So F equal to C by R square. F equal to, I repeat again, F equal to C by R square. So C equal to F R square. So C equal to F R square. So the unit of F is Newton and R square means meter. So this is. So in this type of problem, you have taken the exponent is 1, that is unitless quantity, and e to the power of minus is also 1. E to the power minus is also taken as 1, that is the unit of this one, and this correspond to the dimension meter minus 1. So length, it is the dimension of length, so L to the power minus 1, and Newton means MLT minus 2 and MS square L square, and M L to the power 3 T to the power minus 2. So the exponent is 1, 3 and minus 2 are the dimension, and this is the dimensional formula. So the dimensional formula of these quantities are given. These one and these one are the two answers of question number part A. This is the nuclear attractional force, and the dimension of these and these one are this. So second part, suppose that K equal to 1 Fermi inverse, and that the repulsive electrostatic force between the protons is just balanced by the attractive nuclear force when the separation is 5 Fermi. 5 Fermi. So here you have to take the value of R is 5 Fermi. R is 5 Fermi and K equal to 1 Fermi. So two are same units. So if we placed 1 by 4 pi epsilon naught Q1 Q2. Q1 means the value of charge is given here 1.6 10 to the minus 19 protons. So proton into proton, so square divided by R square equal to this nuclear force. That the formula is given. And this force is equal to the attractive nuclear force. So 1 by 4 pi epsilon naught, this equal to this, or R square cancel each other, and here C equal to, here C, what is the value of C? This is the questions. So C equal to 1 by 4 pi epsilon naught gives us a value 9 into 10 to the power 9, into 1.6 square, that means 19 minus 32 divided by e to the power of 1 Fermi inverse into 5 Fermi. So Fermi and Fermi cancel each other and it remains e to the power of minus 5. So 9 into 10 to the minus 9 into 1.6, 1.10 to the minus 38 divided by e to the minus 5. So this is 3.4 into 10 to the minus 26 Newton meter square. This is the value of C. So C is a proportionality constant. Here C is a proportionality constant, and where the attractive force is, kappa is a proportionality constant. So this power is 10 to the power minus 26, but in attractive force this power is 10 to the power 9. So this is the last question, and I try next day for the next numericals. That is it starts from 16. I will try most of the problems and try to solve as well as clear your concepts with a particular concepts. And today's we show that all the numericals are given in that particular books is depends on the concepts of Coulomb's law, or the concepts of the quantization of charge, conservation of charge, or the NaCl. This is the particular problem that deals with that bonding concepts and the molecular mole concept. And if all the concepts are clear, then why not? You can solve also. So try to solve and try to solve all the numericals, and I also try to solve the numericals given from electrostatics to semiconductor devices. And I think that these episodes or this series you much help you. So I name this episode as the given in the screen first, the numerical king. So welcome to my channel, and this is the numerical king and first day. So first day completed, and I completed 15 numericals. So this is the process how to solve AC Verma. So clear your concepts, and why are you too late? Subscribe my channel and solve all the numericals given here. For the particular session I completed AC Verma. Next I will try Sengage and Eurodov and the Resnick Helides. For the particular session, that's particular DC Pandey will be much more important for NEET or the other competitive exam. For mains you have to choose Sengage as the problem. So all the numericals given their particular books. This is the numerical session, right? It is continued per day. In a week, 2 sessions. I think I completed 2 sessions. That is 15 or 15, 30 or 15 numericals I have completed in 1 week. So if we continue this series, that really help you. So thank you for this episode. Stop.